I'd like to give you an introduction to equilibrium expressions and the concept of equilibrium and Q. So first of all, let's talk about what equilibrium is. Equilibrium is a situation where we have a reaction where we're going from reactants to products, and eventually at some point what happens is that the amount of reactants and products reach a constant value. That constant value can be measured by the equilibrium constant K, which is roughly determined by the amount of products or the concentration of products over the concentration of reactants. On a more exact level, what it is the concentration of each product to the power of its coefficient over the concentration of each reactant to the power of its coefficient, and all of those are multiplied together. Alright, so let's take a look at an example of equilibrium. And here we've got a reaction where we're going from 2A to B, and the A's are red and the B's are blue. Let's take a look at how the reaction goes. Alright, so we're starting off with all reds here, and again the reaction is 2A gives 1 blue. Now what you can see here is we start off with 80 molecules of red and we start off with 0 molecules of blue, and eventually as time goes on the amount of blue evens out at around, looks like about 20, and the amount of reds is going to even out at something like about 50. Now what's going on here is that the number of reds and blues is now constant, because you can see that we've got roughly parallel lines going on here. Now what I want you to do is just follow one of these blues and see what happens to it. We're following this one. And what we're going to see is that at some point this blue is going to switch into 2 reds. So it's going to react. But at the very same instance in the reaction, 2 reds are going to become a blue. So these are not the same reds and blues that we're seeing here. They're reacting and they're changing, but the number of blues and reds is remaining constant, and that's how we're obtaining this equilibrium type situation. This blue doesn't look like it wants to change, but it will change at some point. And you can see all around it, you see reds turning into blues, you see other blues turning into reds as well. There we go, it's gone now. And what happened was it turned into 2 reds, and then somewhere else 2 reds turned into a blue. And it was almost an instantaneous type situation. And this is what keeps the situation the way it is, with a constant number of reds and a constant number of blues. Alright, so that gives us that. Let's go back to our PowerPoint. Alright, as I said, the K value then, and this is at equilibrium once the values have become constant, it's the concentration of products over the concentration of reactants. So what does K tell us? Well, if K is greater than 1, it means there's more products and reactants at equilibrium. And the larger the value, the more products are present. K is less than 1, it means there's more reactants present at equilibrium. And the smaller the value, the more reactants are present. So we're not talking about equal amounts of reactants and products, we're talking about constant values of reactants and products. And we can get an idea of that by looking at the value of K. Another concept I'd like to introduce to you is the concept of reaction quotient, which is Q. Q has the same expression as K, but Q can be used at any time during a reaction, not just at equilibrium. So Q is going to be helpful to us in determining what's going on and where the reaction will go at some point. So again, Q is the same expression as K, but it's going to be used at any other time, including at times other than equilibrium, and it could be used at equilibrium as well. In that case, Q would equal K. Alright, let's take a look at an example of how we could use Q. Alright, so here's a reaction. Let's say we've got a reaction where we've got a Y going to 2 X's, and I'm going to pretend that this is the equilibrium situation. So there's equilibrium right there, and it's only equilibrium because I'm saying it's equilibrium. I can actually go ahead and calculate an equilibrium constant value for this, and here's how it would go. It would be K equals, now it's always products over reactants, so it would be concentration of X squared, and the squared is there because I got the 2 in front of the X, over Y, and Y just has a 1 in front of it, so it's just going to be x squared over y. And what I can do is I can calculate the concentration just by counting up the things here. And we've got 1, 2, 3, 4, 5, 6, 7, 8. So we've got 8 x's, and that'll be squared over, looks like 4 y's, 5 y's actually. So that's 64 divided by 5, which is 12.8. So that is going to be our K value. That's our reference value. K equals 12.8. Now I'm going to take two cases. Now these cases are not going to be at equilibrium, and I'm going to prove that to you that they're not at equilibrium because the Q value we obtained for them will not equal the K value. So this K value is a little bit artificial because I'm telling you this is equilibrium. But here we've got two different cases here, and these are not going to be at equilibrium. So what I'm going to do is I'm going to calculate the Q values for each of these. This will be case A. Q equals, again, it's going to be x squared over y. And the x's will be 4 squared over 2, 3, 4, it's like 7, which is going to pan out to be 2.28. Alright, so there's your proof that it's not at equilibrium. If it was at equilibrium, the value would have come out to 12.8. So it's not at equilibrium, so it's coming to 2.28. Now what we can do here is we can ask the question, well, which way is the reaction going to go? You've got to remember that when a reaction is not at equilibrium, where it wants to be is equilibrium, and that's where it's going to head. So currently the value of Q is less than the value of K. So the reaction is going to do everything it can to make sure that this value increases so it gets to K. So Q is less than K. And in order to get to K, what's going to happen is the numerator is going to have to get larger. Now the numerator in this case is the products, so the reaction will shift towards the products. The other way of looking at it is you can say it's shifting away from the reactants, because also, as well as making the numerator larger, you could also make the denominator smaller. So you can make x larger or y smaller, but that's what's going to happen anyway. If x is large, x is getting bigger, y is going to get smaller anyway because the reactants are becoming products. So the situation will be that the reaction will shift towards the product. So that always happens if Q is less than K. Alright, let's look at this situation here. Again, we've got our Q value. It's going to be x squared over y squared. Oh, sorry, x squared over y, I mean. And we're looking at, now, let's see, there's 1, 2, 3, 4, 5, 6, 7, 8. There's 10 there, 10 squared. And there are 4 y's, so it's 10 squared over 4, which equals 25. Now you can see what's happened is that Q is now greater than K. If Q is greater than K, now the reaction will shift towards the reactants. So to reactants. The reason for that is that we have a value of Q that's larger than K, so we're going to have to do something to lower that value. We can lower that value by increasing the value of the denominator, or Y, and decreasing the value of X, which is the product. So the reaction is going to shift toward the reactants to decrease the value of Q and bring it closer to K. Alright, so if Q is less than K, then what's going to happen is the reaction will shift to the products so that the value of Q can become closer to K. If Q is greater than K, then what's going to happen is reaction will shift towards the reactance so that Q can become closer to K. Remember that Q's aim will always be to get to what K is.